Hello everyone, welcome back. So, today we're going to be talking about axial deformation. You're like, well, we've already talked about this a little bit, but this is different because we're talking about determinate and indeterminate systems. We want systems of bars now, not just one bar by itself, but also where the deformation of other bars will be affecting that bar. Now, this is a bit different than we've done in the past, in the fact that besides my application section, I'm not going to be showing you any extra examples or group problems like normal. Those aren't going to happen because they're actually going to be connected to each of these topics. So you'll see actually more examples this time because of that. The reason I'm doing that is simply because these concepts are best taught through example. You need to see how it works to understand how to do it. So first off, let's talk about application. Now, Greeks were amazing. I'm not sure if these are actually Grecian columns, but they made these amazing structures. They're held up by these beautiful columns. Now, these structures are not perfectly uniform, especially these days. And so because of that, each of these columns has a different load, and its deflection is going to be different. So if we want to figure out what the deflection of the roof is going to be, like if I'm going to build something on top of it, I would need to understand how the deflection of all of these columns is going to affect that. I can't just look at one and say, well, that's the answer. No, all of them are going to be different. And so they're all going to affect each other. Okay, so many structures are very similar to this. They're going to have multiple axially loaded members, kind of like this one right here, which we're going to work through. And so we have to figure out how we can figure out the deformation of the system of bars. Now, in some cases, it will be something called statically determinate. That says simply that we can solve it using just our equilibrium equations. We don't have to worry about anything else. Our equilibrium equations, those will be enough. And so we're going to focus on an example now, which is one of those statically determinate examples. So what we have here is an assembly, and it's got a rigid bar A, B, C. And there's two fiber reinforced plastic rods on the sides, and a fiber reinforced plastic post in the middle, with their areas being shown here. The modulus elasticity for those rods is as follows. We want to find the deflection of this point D. How far does it move after applying this 30 kilonewton load? Okay, so if you want to, you can go ahead and try this on your own. Feel free, but otherwise we're just going to go ahead and do it together. So, first thing you're going to do is draw a free body diagram. And here it is. This is my rigid bar, and I've got three forces going down. Force 1, Force 2, and Force 3. And quite obviously, one of those would have to be going up, because otherwise it wouldn't be in equilibrium. We're not going to worry about that too much right now. And now we're going to write out our equilibrium equations. Well, what you can already see is there is no force in the x direction, so our sum of the forces in the x direction doesn't really help us. This might freak you out. You might be thinking, okay, we've got two equations. We've got 1, 2, 3 unknowns, so we can't solve. We're stuck. Well, if that was all, yes, we would be stuck. However, we can also take these individual members and figure out equilibrium equations for them too if we know something else. So I'm going to draw a free body diagram of this rod over here on the right, and I'm going to look for some easy stuff. Well, that rod on the right, it's pretty simple to say that there's only two forces. There's force 3, and there's P going down, which means that force 3 is going to be equal to P, and therefore it's 30 kilonewtons. And with that, we actually get to avoid all of our algebra altogether, because we can just plug in that for force 3. So let's solve for force 1, and we can plug that in here and here, and we can solve for force 2. So we don't have to do really any algebra, we just have to be careful to plug it all in the right place. And what do we get? Well, we get that force 1 and force 3 are this, and force 2 is negative. It'll be negative 52.5 kilonewtons, so it should have been pointing up. Okay, it should have been pointing up, because it is in compression, not in tension. Now we're going to determine the force deformation relationships. This is that Flee equation. You've seen that before? We know what the area and the elasticity is. We know the length of the rods, and we know the force. And we can figure out how much each of them deform. Now, you can check these numbers if you want to. The big and important thing right here is the following. Notice how they switch from gigapascals to megapascals, and from meters to millimeters. and from kilonewtons to newtons. The reason they're doing that is because 1 megapascal is equal to 1 Newton per millimeter squared. And so that's just a nice little relation to remember. You want to memorize this. It makes things a lot simpler on you. Okay, so what we see is that the rods both get longer and the post gets shorter by 7 millimeters. Now, is that enough to solve? Well, yes it is. However, it's not immediately apparent how we solve that, because we're not caring about delta 1, delta 2, and delta 3. We want to know how far this guy moves. That's the deflection. And that's going to be equal to the deflection of point C plus how much that rod stretched. So what is it? What is it going to be? And how do we solve this? Well, the big important thing to remember is that the slope of this rigid bar is constant. And through some similar triangles, we can actually solve for VC. So first thing we're going to do is we are going to set up this little triangle right here. And what we see is that over a distance of 2.4 meters, it goes down by the length of VB plus VA, which is 16 millimeters total. If you're wondering, like, one of them was -7. Yes, it was, but that was from here. So that's just, we're going to say 7 right now. And yes, it is 7 going down, but for this, we're trying to find out the side of the triangle. So it doesn't matter too much. Okay. And then we're going to set up a second triangle, which should have the same slope. And we see that this one over here, we can't quite figure it out yet because we don't know what our deflection at C is. But we can make up this a second equation. So we know that 9 millimeters, which is VA, plus this deflection at C over 4.2 millimeters is going to equal the slope. And both of those slopes are the same. So if we use that, we can solve for the deflection at C, which would be 19 millimeters. And since the elongation of this rod, delta 3 was equal to 10 millimeters, our deflection at D would be 29 millimeters. So this similar triangle thing, it's very, very important. I'm just going to say that that's one of those skills you're going to have to practice as you go through. You're going to have to learn how to see the trig to make sure that it works properly. Because otherwise, it can be a pain. So don't forget to look for the trig in here and look for the slopes that are the same, because that's how you're going to solve these kinds of problems. So that's it for this one. Thanks for listening. And next time we'll go into some complex systems of bars. Like, wasn't this complex enough? It was, but we had the nice fact that they were all, in parallel to each other. Next time we talk about bars that are not parallel, that they're connected and they're going to be angled, and it gets all kinds of craziness. So I hope this helps you, and I'll see you all next time. Bye-bye.